Good morning, all. Good morning, Sudhagar sir. Welcome, sir.
Good morning, Deepa ma'am.
Thank you, sir. Sir Dundi, sir.
Yes, ma'am.
Now it's 9:30. Shall we wait for 5 more minutes, sir?
It's okay, ma'am. It's okay.
Yes, sir. Thank you, everyone, for joining. We will start in our session in another 2-3 minutes. Dundi sir, able to
Yes.
hear me?
Yes, ma'am. I'm able to.
Shall we start our session, sir?
Yeah, ma'am. Sure.
Okay, okay, sir. Thank you.
Okay.
Good morning, all. It gives me great pleasure to extend to a very warm welcome on behalf of Department of Electronics of Kochi Institute of Science and Technology to the fifth day of Phase 3 of the AICT-sponsored 6 days short-term training program on the topic Trends and Technologies in Antenna Design and its research scopes. Today's session on the topic Flexible Antennas, Design and Implementations by Mr. Dundikumar Janpala. Mr. Dundikumar Janpala received his Bachelor and Master of Technology degrees from LBRCE, JNTUK in 2011 and 2014 respectively. From April 2018 to March 2020, he was a junior research fellow in a DRDO funded project, and currently he is working as senior research fellow in DRDO funded project and pursuing his PhD in electronics and communications engineering at Karunya Institute of Technology and Sciences, Coimbatore, Tamil Nadu. His research interest includes flexible antenna development, wearable technology, sensors, metamaterials, solar cell, energy absorbers, medical antenna, microwave and RF components, package antenna, UWB, fractal multiband, DRA, and reconfigurable antennas, and developing materials for soft electronics. He authored or co-authored 5 reputed technical articles. We welcome you, sir, to our STTP program, and over to you, sir.
Thank you very much, ma'am, for the nice introduction. I'm trying to share my screen. Can you able to see my screen, ma'am?
Yes, sir. Yes, sir.
Okay, ma'am.
It's getting loaded, sir. Yeah,
Okay,
it's
ma'am.
there. It's there.
So is it moving?
Yeah, can you put it in a slideshow?
Yeah, I will show.
Yeah, slideshow is there. Yes,
Uh,
sir. It's good.
okay,
It's good.
okay, ma'am. Good morning, one and all. Today, I myself is Dundi Kumar Janpal. I'm from Karunya Institute of Technology from Coimbatore. Today, I'm going to take session on flexible antennas. It's a design and implementation. So the facilities we have here on in our institution, we have several simulation tools like electronic suite ANSYS 19.2 version, and we have FICO, NAWR, COMSOL, MATLAB, a lot of other things too. And we have network analyzer, 2 network analyzers we have, and we have some setup for making polymers for flexible substrates, like for sensors or antennas or flexible PCBs. We have that facility too. Um, so actually, mainly I work on these things. Occasionally, some other things I will work. So these are the things that I mostly spend my time on. So and these are the members of my team. And so she, Nasisuda ma'am is my professor, and Jaiba Singh sir is the professor from chemistry. Is the one who helps me with nanoparticles and all. And this is I want to give you a glimpse of what kind of research we do. So these are the 2 published works, prototypes I kept here, and the second one is by far the smallest antenna that I've made. And these are the polymers we made to use as a substrate for our flexible antennas. So some are replicated from others, and some we developed on our own. And some natural based resin based polymers also we made. These are all for usage for several applications, not just for antenna. And today, my aim mainly I will be concentrating on taking a session, my entire session. First thing I will address what is the complication a researcher will face while making a design, bending design. So there are few things one needs to address so that you can start your bended design, and you can compare, that complications when answered only you will understand how it is done. And then next thing is, whenever I say flexible antennas, there are several flexible materials are there. I want to stress on importance of how the polymers play a vital role in flexible antennas, how you can make your own polymer, and how to not only I'm going to tell what to do, I'm going to show you how to do with a live demonstrations too. And and I will show you how to characterize them, and I mean like how I will tell you how your conducting parts can be added to your antenna, the fabrication the implementation complications, and some research gaps, and what are the other things you can add to your research. Everything as a complete thing I will discuss in this session. I hope the entire time permits for the entire show. So first thing, for anybody to start their design, you are all maybe aware of doing an antenna design in a flat condition. But when you go for a flexible design, most of the people will just take a hollow cylinder with some thickness, the thickness of the substrate that you want to do, and they will just wrap their sheets in the simulation tool and they will take it. But it is not proper bending. And another thing, another common mistake people will do is they will take a bend shape, but where the length of the antenna is not equal on the top side and bottom side. There will be either excess of substrate available in the design, or you are going to cut a little bit more than what you used to cut. So it is like you are making a mistake in your design itself. So when you fabricate it, obviously your simulator and measure results, and they will be no longer in the good agreement. So it is must for any person to make a proper flexible design without any error. So your length on top side and bottom side should be accurate. Then only you will get proper bended design and you can match. So this is one thing you should be taking care of. So there are few things that you should take care so that your simulated and measured results will be in good agreement. So this is the first thing that we need to discuss. That is, suppose here you can see this is the length of my substrate and the h is thickness of my substrate. When I bend it, so so I am going to take a center line here, L by 2, L by 2. Similarly, top also should be L by 2, L by 2. Then only it will work. What I'm trying to say here, if your bottom length is bigger than what it is supposed to be and the top length is exactly what it is supposed to be, that means in bottom side there is an excess. And some people will cut in a way where bottom side L is accurately it will be there, and top side there will be little excess point. This should be addressed first, then only you can get the design properly. So I will go to second slide and come to the front slide again. So you can see here, suppose I'm taking a circular, hollow cylinder shape, and I cut it into the middle. Now you can see, obviously the inner radius, whatever the inner radius, this length, it is lesser than the outer one. So as per your length, this is the excess part. This is the excess part you should remove while designing. When you remove that part only, then you will get the proper design with accurate, your length and as well as the thickness. So here I will show you. Suppose I have taken some radius. I'm trying to cut it. If you cut slightly with this line, then there is a excess part here. If you cut slightly in this line, then there is some part you are cutting extra. So either if you are following this line, you are leaving some little bit extra point. If you are following this line, you are cutting little bit extra point. That means you should not go in this manner. You have to only separate this part and leave this part. Then only it will come accurately. How exactly you can do that? So now the calculation is here is, now you take here center, this is your radius. Actually for overall diameter I took r, so my radius is r by 2 in this calculation. Now you can see this is the bending radius you want to take. So most of the literature when you see, you will be looking at like the bending comparison, flat and bended to 50 mm, bended to 60 mm, and this comparison you will give, and you will show. So when my antenna is flat, this is the reflection coefficient I am getting. When my antenna is bended to 50 mm, this is the reflection coefficient I am getting. This is how you present this particular comparison in your article. Now, so this r is my bended radius. Then you are only aware of three things here. One is radius of bending you want to go, and the length of your substrate, and the height of your substrate, the thickness of your substrate. These are the three variables that are available to you. Based on that, how you can calculate these coordinates so that you can enter into your simulation. That is what this is about. Now here, exactly this coordinate you need and exactly this coordinate you need. How? This coordinate, so this is total L and this half part is L by 2. So this is L by 2, okay. And this point, when I draw a line here, the angle is theta 1. So for bottom one, I am representing as a 1 dash. For top coordinate, I am representing as a double dash. So this is r by 2 radius because I have taken diameter as r. So you can take it as r if you are calculating. So this is radius, this is theta 1, and this is L by 2. Now what I want here is, if you draw a straight line here and you draw a straight line here, this is x coordinate and this is y coordinate, then this is a y1 and x1. So how you are aware of this particular radius, you don't know the angle, but you are aware of this length. The how you will calculate your angle is theta 1 equal to this L by 2, whatever this arc length, L by 2 by radius, R by 2 into 180 by pi. That is your angle here. So first you are going to calculate that. Based on this angle, once you know the angle, you know this h hypotenuse, and then you will be able to calculate easily x dash and y dash. Y dash equal to r by 2 into sin theta dash, and x dash equal to r by 2 into cos theta dash. So now you have the coordinate for x dash and y dash. Now in order to calculate theta 2, here radius is your r by 2 plus thickness of your substrate. That means r by 2 plus h. So your theta 2 dash. Now see, what is happening when you are following a straight line is, here L by 2 will come extra, but here we are taking exactly L by 2 here. L by 2, because top also it is supposed to be L by 2 only, bottom also it is supposed to be L by 2 only, then only your top length and bottom length are accurate and your bending is accurate. So theta double dash equal to L by 2 by R by 2 plus H. You are adding the thickness of the substrate here to your radius into 180 by pi. Similarly, Y double dash and X double dash. So this simple calculation you have to perform, so that you will have the exact coordinate of this one and this one, so that you will have the exact bending. So this is what removing this part exactly. You are not removing a part extra, or no, you are not leaving any extra part behind. You are exactly calculating and bending it properly based on the thickness and length you have chosen for your design. So this should be performed and taken care of while you are starting your flexible antenna design. This is the first complication that I wanted to address. Now I'm going to, normally this particular complication itself I will take 2 hours to explain, but I will try to short it and try to finish it in 20 minutes, and so that we can cover the remaining all things. So please kindly bear with my fastness. So here I will try to give you a glimpse in practical way. I mean, like directly I will show you in the tool. So this is our tool, ANSYS 19.2 version. We have our institution academic research version. So are you able to see my screen, all of you? Software?
Yes,
Hello?
sir. Yes,
Okay.
sir.
Okay.
Yes.
Thank you. So I will simply start a little bit. I will go a little bit faster, hoping that you all are familiar with the simulation tool. Suppose I'm going to draw a substrate, and then I am drawing a patch, and then I am drawing a field line, strip line, and I'm drawing a ground part. So these are the parts we have in our design. Now here, so box substrate I am giving. I'm not changing any material or anything because I want to show you the complication directly. So I'm going to take this one a little bit. So this is my substrate. I'm trying to give minus 50 comma, sorry, I will take 25, minus 25 comma, and minus 25 comma 0, 50. So some 1 mm or 2 mm, you take whatever thickness you want. So control D. So be here, please see this here. The green one is Y, and the blue one is Z, and this red one is X. So obviously opposite to these lines are negative values. So this is positive Y, this is negative Y, and this is positive X, this is negative X. Upwards is positive Z, and downwards is negative Z. So I have given the coordinate minus 25 comma minus 25. That means I am starting here, and I have given X dimension as 50. So I ended up to 50. And again Y also minus 25, and the size is 50. So the antenna is equivalent in all directions. So 25 this side, 25 this side, total 50. 25 this side, 25 this side, total 50. So I am trying to take symmetrical one. So I mostly I will go with symmetrical, or otherwise I will go selecting only one portion. Now here I'm going to take minus some 15 comma minus 15 comma 1 mm. Thickness I have given 1 mm, so I am going to give 1 mm here. 30, 30. Okay. Here I am giving some minus 1. I'm going to give a width of 2. So I'm giving minus 1 here. So 15. Um, 10. This is 2. So I'm going to unite this one patch and rectangular. So here you will have unite option. So this is how you will do your patch antenna, and this I will give you ground. So this is my ground. So partial ground I have taken. So this is how you will do your antenna. So if you are, you since you kept antenna like this, you will do port here. Otherwise, if you are starting from here, stipend, you will do port here. So why I am saying this port here and port here is either you will bend your antenna in X orientation or you will bend your antenna in Y orientation. So while bending, you have to be clear how you can bend in X direction and give port here, and you can how you can bend in Y direction and give port here, because port calculation here is different than port calculation here. So this is a simple design I have done, but how I'm going to bend this with the exact dimension is the complication that most of the people will face. So normally what people will do is I'm going to hide this entire thing, view, hide selection. I'm hiding this one. So what majority of the people will do is they will simply take a particular cylinder they will take. So what they will do is they will put it, I will put it at center 0, 0, 0, and probably I will give here minus 25 because we are doing equivalently. So radius I am going to give some 50 mm, and height I am going to give some 50 mm. So this is how they will take a cylinder, and then what they will do is Control C, Control V, and they will take 2 mm extra thickness of radius. So suppose 1 mm, if you are going for 1 mm thickness. So cylinder 2, cylinder 1, and subtract and press OK. So what people will do is they will take this portion and they will take one particular, sorry, not in this plane, XY plane. They will take a sub patch here and they will take minus 15, comma, minus 15, comma, maybe probably 100 or more. So 30, 30. So they will select this cylinder and they will select this particular rectangular and they will go edit, surface, wrap sheet. So you can see here, this is how they will wrap the sheet. But taking this entire part and doing your work, it may not be proper. Most of the people will follow this. And one more complication they will do is they will take skin, fat, muscle, bone for SAR calculation also in this way, and they will try to compute that. But it will take a little bit higher resource for simulation, and it will take some time. Now I'm going to show you how this entire thing can be done as per our exact dimensions, by taking one of my already made designs. So here you can see this is exactly with whatever dimensions I choose, this particular design will adjust itself. So if I enter some value, if I need a 50 by 50 length and with thickness 1, it will adjust itself. If I need 100 by 100, it will adjust itself. So whatever the value I enter, it will adjust itself. I will show you that HFS is design properties. Suppose radius is 50, I want 50 mm length and 50 width and with thickness 1. Are you able to see it, how it's adjusted itself? So I have done only one time, I made calculation and made this one. Now I can use this for any design I want to do. I can use I can assign any material I want to work with for this particular design. Only one time I made it, and I can use it for n number of times. So now I'm going to dismantle it and I will show you in a separate manner so that you will understand how I did it. So here I'm going to dismantle it slowly. So this is the extra parts that I have been talking about. See, you can see this is the extra part. If you are cutting this part only, your the bend is accurate. So I'm going to remove one by one and show you. So this is how I started my design. First, see cylinder one. This is the first cylinder I have taken. Then I have taken one more cylinder. So based on the substrate thickness. So the difference between the cylinder one and cylinder two is the thickness of your substrate. So I have to consider this one first. So now once I eliminate that part, I subtract that part. So I will be having first is I will be having a hollow cylinder. Once I have this hollow cylinder, I am going to take a box, first box, half part I am cutting. So one box I have taken, which is covering my entire particular substrate. So then I have removed that part. So now this is what I am getting. When I'm at this juncture, what I did is I took separate planes. So I have taken for this particular point, I will show you. I will remove this unit. So you just see here sheets. First I have draw this point, then this point, then this point, then this plane. So each plane I have drawn separately, then I united them, then it will become a box. Then it will become a box. Similarly, when you design at negative y side and you want it into positive y side, what you have to do is you just have to control C and control V and you will get this one. There, instead of for y coordinate, everywhere for y coordinate, you just add negative to positive. So you just shift the negative value to positive value and this particular part will come to you. Now here, how I did,